All right, so chapter 5 is called Curve Sketching, and we've been learning all sorts of things leading up to chapter 5. The characteristics of graphs, increasing and decreasing functions, right? What's happening to the derivative over certain intervals? What are maximum and minimums, and things like that. And so we're going to kind of keep continuing on exploring more characteristics of these graphs, and what do we know about the graphs using calculus methods, and how can we piece all that together to sketch the graph kind of without technology. So just given the equation of the graph, how do we know what the characteristics are and how can we sketch that? So that's what chapter 5 is all about. By way of review, so if you look on, I guess starting on page 204 in this textbook here, they talk about intercepts. So just some review concepts here that we would want to know before we get going on the actual calculus. Intercepts, okay? This might seem very basic, but when we talk about intercepts, y-intercept, for any function there's only ever one y-intercept, right? Doesn't matter how crazy the function is. If it's a function, it should only have one y-intercept. Okay? And of course, in order to find the y-intercept for any function, we simply let x equals 0 and then solve for y. And so an example here would be if we had y equals 25 minus 4x squared, let's say. In order to find the y-intercept, you just go ahead and plug 0 in for x right here, which makes this y equals 25 minus 4 times 0 squared. And of course, that is y equals 25. So in this particular graph, the y-intercept is 25 because that's the partner coordinate. If x is 0, then we know that y is 25 because this coordinate should satisfy this equation. The x goes there, and that y goes there, and that should make sense. Okay? So we could graph that as well if we wanted to. And so we turn your graphing calculator on if you have one. If you want a graphing calculator, for now, just to kind of confirm some things, go ahead. Just take Okay, so if we plug that in, you guys have something here. Get rid of this, and our function is 25 minus 4x squared. So again, turn it on, y equals, make sure everything is clear, make sure your plots are not highlighted, plug it in, hit graph. Okay, so right now we can't see the y-intercept, right? In this particular window, it appears that this parabola, because it's a quadratic function, degree 2 is a parabola, it appears that it goes higher than what the screen is showing. So you can fix that by hitting window, and you can change your y maximum. We want more than 10, don't we? We're thinking that we need at least 25, right? That's what we're thinking. So let's say 28, and let's see what happens. There we go. So the graph is, hitting the axis there. It looks like about 25. And if you wanted to graph or calculate, see, second function trace is the calculate function, and you might remember doing this from pre-calculus. But if you want to calculate a maximum here, you hit 4, and then it will ask you left bound, question mark. So you move your cursor over so that you want to create a left boundary. Hit enter. Move your cursor over. It's asking you for the right boundary. So anywhere on the right side of what you're looking for to be a maximum. And then because some graphs may have several maximums in the picture, you might want to move your cursor close to that and then hit enter. And then it should calculate what the maximum is. So x equals, now this is a strange number, isn't it? But 2 times 10 to the negative 6. Really your calculator is saying, hey, that's 0. Okay? Remember, your calculator has to pick one point out of an infinite number of points, right? So it's it's trying to get 0. Sometimes it does show exactly 0. Sometimes it just grabs a point that's super close to 0. But if you see something like this, you can just assume that's 0. And of course, the y value is 25. Okay? So that means 0, 2 times 10 to the negative 6, and then 25. Okay? The X-intercepts are much the same, except opposite. Okay? So X-intercepts, you let y equals 0 and solve for x. Yes?
For the x, for the y-intercept, why don't we just state value that x equals 0?
Yeah, that's what you would say. Yeah, x equals 0. Oh, yeah, you could do that too. Yeah, you could plug in. You could do value too. Yeah, you could do value as well. X equals 0. Yeah. But for the y-intercept, you can. Yeah. I guess I did that so that you could find the maximum whenever you needed to. But yes, you could put an x equals 0 for a value as well. Okay, so let's say we have the same one, 25 minus x squared, and we let y equals 0. And if we come up to this point, we say, oh, let's see here. I've got x over here. I'm going to want to try and solve for x. And so you bring it over to the other side at x squared. And x comes to plus or minus 5. Okay? And that, so mathematically, we have x plus or minus 5. If you want to go back to your graph here, it appears that that might be, okay, plus and minus 5, but let's, oh, okay, yeah, so this is not the same one. Okay, so let's do this different one. That's fine, thank you. It's not the same one that we did, so why, let's do just, let's delete that and make it the x squared. So this is the new graph, and there we go. So negative 5, if you count that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, those are the x-intercepts. And just as a refresher, if you need, the second function calculates, if you want to calculate intercepts, those would be the zeros. So you hit 2 there, and then again, you could do this individually. Your left boundary, if we wanted to find this one over here, you can go anywhere in this region. Yes, left boundary, and then right boundary, yep. So that you have the boundaries kind of on either side of what the 0 would be. It says guess, you hit yes, and 5, 0. So there's, you can find that as well. If you wanted to check to see if this does yield 0 again, you could do the value thing as well and just plug in 5 or negative 5 and see if 0 is yielded. So anyway, so that's basic intercept stuff. That's pretty basic. Okay, so we good with that? Okay. Oops, that's not what I want to do. Okay, so the other thing we want to do here is we want to look at symmetry. Okay, so this is going to be a big deal. This is not really calculus, but this is symmetry. So there are two types of functions that have symmetry, and those would be even functions or odd functions. Okay? Even functions and odd functions. If they're not even or odd, okay, not every function is either one of these, not necessarily, but if they are even and if they are odd, they have a certain symmetry about them. So let's first explore even functions. Now, I don't know if you remember this at all, but if you have a function and you put a negative x in, so some value for x that is negative, let's say negative 1, then that should have the same value, if it's an even function, as f of positive x. Okay, so these two should be the same. If it's the same value, doesn't matter if it's positive or negative, it should yield the same y value. And an example would be, can anyone think of an example? Well, what about y equals x squared? If you put in a negative value for x and you square it, you get the same value as you put in a positive value, right? And so if we tested that, y equals negative 1 squared, and we also tested y equals positive 1 squared, we would of course see that both equal 1. So they're the same, even. Now an even function has a symmetry about, now when we say about, that kind of means around or surrounding, about the y-axis. So the y-axis would be the point, or the line of symmetry. And of course, y equals x squared looks like this, right? There's 1/2, and here's the other. It is symmetrical about the y-axis. A -1 value has a +1 value for y. A +1 value for x has a +1 value for y. So symmetrical about the y-axis. Questions? All right, odd functions have a symmetry as well, and let's describe what they look like here first. So if you have a function and you plug a negative value in, an odd function will look like this. Negative value for x yields the negative version of what the positive value would yield. Okay, so it's slightly different. Slightly different. We have the negative outside. Okay. An example would be y equals x cubed. That's a simple example. And why would that be? Well, if you have y equals -1, and you plug that in, then that's cubed, and so y equals -1. Okay? If you plug in a +1, so here's the negative x, the positive x. If you plug in +1, you would get +1 as a value. And of course, if we did this, put a negative out front, which would cause this to be like this. Now you see how they are equal? So once again, this is an odd function because the negative x versus the positive x, one is positive and one is negative. Questions? The symmetry, it is symmetrical about the origin. So it's not a line that it's symmetrical about. It's symmetrical about a point. So let's see if that makes sense for y equals x cubed. Well, there's our coordinate plane. Here's x cubed. This is the function roughly, right? Okay, that's sort of what it looks like there. Rough looking thing. Now, symmetrical about the origin, that means that if we were to somehow rotate this entire graph, if we spun it around the origin, eventually, within one turn, it should map onto itself. Okay? And so, if you just, sort of watch my amazing graphics here, but if we have, like this, and then it goes on like this as it moves, closer. This is going this way. This is going this way. This is going this way. So then it will eventually map onto itself as we spin it around the origin.
Does it have to be in 180 degrees?
No, it does not. It does not have to be a 180-degree turn only. Nope, nope. If you had some sort of if it's going to be a cubic function, a cubic function that is odd, then it'll probably be, I think, 180 most of the time that you do that. And if it's a function, I don't think it will really work less than 180. So if it was sort of like this x right here, then you could spin it maybe 90 degrees and it would map onto itself maybe, but that's not a function then. So if you have functions like, this, right? That's going to be a 180. A lot of cubic functions look like that. So 180 is kind of your big one, yeah. But what you will be able to tell is that it will have some symmetry about the origin. So if it's an odd function and you're only given part of the graph, or you can only determine part of the graph, you will know that everything around that origin. So let's say it looks something like this, okay? And you know that this is half of the graph. Well, if it's odd, it's going to be symmetrical about the origin. So this is going to be a little tough to graph, but you take each little piece there, this little piece, okay? It's going to be the same. So that